So today we'll be hearing from Andreas Putz, who's a scientific computing expert and data analyst at MistyWest, focusing on creating intelligent connected devices. His special interest lies in thoughtful application of machine learning to real-world client problems. MistyWest is an engineering design consultancy that creates new technologies to enable healthier and more prosperous planet, with a focus on projects advancing UN Sustainable Development Goals. So without further ado, thank you.
Okay, thank you so much, and thank you all for joining this talk. I know going to conference talks and COVID times is somewhat strange and looking through all these video lectures. So it's strange listening to them. It's also strange giving a presentation without an audience. So I will see if I can do my best. As I'm giving a talk about machine learning and embedded devices, I should better use one. So I better do that now. Alexa, set timer for 20 minutes.
20 minutes, starting now.
Okay, so hopefully Alexa the edge will work and it will give us a reminder in 20 minutes that it should stop talking. So as you can see from my beginning slide deck, we are going to talk on one hand about the cloud, on the other hand about the edge. So cloud computing and machine learning and cloud instances has been around for quite a while, and it's a pretty familiar playground by now. The edge has been around for a while as well. Some people say the edge has been around for forever as well, because you had small distributed devices before. But a lot of things changes when you try to do machine learning and inference on the edge. And actually, a lot of things changes when you have machines which are on the periphery and you would like to keep them updated. You would like to update your models frequently. Things are not as nice. Like you're exposed to the elements, it's cold, it's hot, you're exposed to sunlight, it might rain. You might not have power. You might have to rely on a puny battery, and connection might be bad. You might have to talk to a satellite. You might have to talk to Wi-Fi. You might have to talk to LTE networks, and you might have to talk to multiple things to get you connected. So that's going to be today. A little bit of a background about me. So the introduction was already quite nice. So I'm the discipline lead for software and data science, and also for internal projects at MistyWest. Being the head of internal project means that I can also spend some time to explore things on the computational side. So we have a small little computational platform called RoboSteve, which has NVIDIA TX2 typically on board, or Xavier. And we use this to kind of prototype our deployments. I also have with that the chance to always play a little bit with math. So I've added the Mandelbrot set to it, and I do a couple of open source projects. One of them is OpenPNM, which is a poor network modeling tool, which is strangely related to neural networks as well. And I do OpenFCST, which is a simulation toolbox for hydrogen fuel cells. So you already heard the story about MistyWest. So you're a product engineering partner, and we're trying to bridge the gap from lab to assembly line for specifically intelligent connected devices. And we'd like to work ideally in an environment which kind of tries to further the UN sustainability goals. And typically we do a lot of firmware engineering. We do a lot of electrical engineering, so embedded systems architecture, like putting typically systems on the chip. And to a more general design, we do sometimes FPGA design, and we do a lot of custom camera design, and specifically a lot of custom sensing design. And to round this off, we do a lot of mechanical engineering about this, industrial design, software engineering, and also we do front-end research and development, mathematics, physics, a lot of optics and lens selection and spectral imaging. Okay, let me start with some motivation of our problem. So I have two case studies where customers came to us with an idea and they needed an intelligent ad platform. The first one is a company which wanted to build an IoT-based occupancy monitoring platform. And that means they would like to detect how many people or how many human beings are within a specific area of view of your camera system. But they had some requirements on that. So traditionally, you would create basically a webcam. You would stream the webcam footage to the cloud. You would run your image processing, YOLO, or whatever you want to run on your cloud backend. and you would feed your backend application with all the detection your backend application did. Our client was working in an environment where it's not allowed or not desired to stream image data of the device. So what they would like to get out of the device is just how many people are in the volume, how many left, how many entered. And that is it, no more, no image data, no additional data. And that was other methods would have violated privacy rights of people working in this environment. So, and this is one thing we see a lot, that privacy requirements will lead to legislation that you cannot actually just stream all video data off the device in sensitive areas. So now you need devices which can generate this information directly on the device. And with that, you need strong and more powerful local hardware, and you need to be able to load machine learning models, load AI and ML models in a comfortable way onto these devices. Typically, you run these devices in two modes. So you have a room where you can actually stream data off. You use this room to generate your training data set. And then you have your deployment devices. The deployment devices have the streaming disabled, and they can only stream the meta information. How many people are in the volume, how many people have left per time unit, how many people have entered per time unit. And that was one of the possible applications of edge compute. The other problem we had, the World Wildlife Foundation was coming to us, and this is a problem where we haven't implemented ML on the edge yet, but it's the next step to do. So they came to us saying that the last generation of trackers for polar bears is now, I think, 20 or 30 years old, and it's really an uncomfortable system for the polar bears to wear. It's basically a shoulder harness, and the bears can strip those off pretty easily if you design something which the bears can wear. It's a pretty burdensome device. So what the idea they had is, instead of having that shoulder strap, they would actually like to give the bears either an earring or kind of a hearing aid looking thing, which clips in a little bit around the head and around the ears. And that device is supposed to be able to send vital data, but also precision data of the bear. And we built such a device. And actually, this thing can talk to Argos. So it talks to a satellite network because there's no Wi-Fi in range. So we actually have a somewhat large thing which can attach to the ear, which can talk to the Argos satellite network. And at the moment, it transmits, I think, temperature, GPS position, and accelerometer net data. The challenge of the solution was that to make it small, you can't put a big battery in. If you can't put a big battery in, you don't have a lot of power for compute, and you don't have a lot of power for communication. So you try to send as little data to the network as possible. But with that, you lose granularity of your measurement data. So one of the ideas going forward is to have a local, small, extremely low power ML unit, which you can use to generate pre-processed data, and you actually send the pre-processed data instead of all the raw data to the cloud. That allows you still to reconstruct the same movement pattern and the same activity pattern without having to send the same payload. Yeah, so a simple example of something you can easily purchase is the Google Voice Kit. So this thing runs the Google Assistant in a similar way as Alexa just ran Alexa. It has, Alexa just is trying to start up. So this thing is a Raspberry Pi.
I don't know that.
Thank you, Alexa. So in this case, Google has created a little plaything which is based around a Raspberry Pi. In fact, around the Pi Zero, which is in the middle of all of this. And it's a very, very basic edge device. And the way it works, you hit the button turns on the microphone, you speak, you release the button, that speech piece is going to be sent to Google. The Google API translates it, creates an action, and sends a reply back to the speaker, and the speaker gives you the reply. So it's not really doing any edge compute. So the question is, how much can you actually do on the edge, and how much can you actually take back from the cloud and put on local devices? Some of the buzzwords, there is now people talking about cloud, fog, and edge. I typically don't distinguish between cloud and fog, except in very rare cases. For me, it's basically cloud and edge. I haven't really had a case where you really had to dedicate a talk to something in the fog, which are typically gateways, network infrastructure, or some consolidation servers. It's interesting if you're in an environment where you have a hybrid cloud environment, so where you have a local compute center as well as the cloud, then that fog layer sometimes is part of the hybrid.